Good morning, everyone. Thank you for the warm introduction. My name is Princiya, and I'm a software engineer working at a digital health tech product based out of Berlin for a company called Smart Helios. I started my open source contributions through Outreachy, which is a program to get more underrepresented people into open source. I deeply care about diversity and inclusion, and I volunteer my free time for programs which focus on getting more diverse people in open source, such as the Node.js mentorship program, the open source maintainer leadership cohort program, and recently, with my involvement in today's topic, I am hooked into privacy and security. You can find me on GitHub and Twitter for more questions. So upcoming is a brief introduction about web tracking, about this open source browser extension called Lightbeam, which I built during my Outreachy internship last year. All the visualizations to learn about the first and third party trackers, and with a dash of open source. Lightbeam is a privacy browser extension that visualizes the connections between sites that you visit and third parties that might be tracking you. It works by listening for, capturing, storing, and ultimately displaying the results made by each website as you visit the web. When you activate Lightbeam and visit a website, normally called the first party, the browser extension creates a real-time visualization of all the third parties that are actively involved in that website. As you then browse to a second page, it highlights the third parties that are also active there, and it tries to form a connection between the websites that you visit, ultimately the graph growing into a heavy connected graph layout. I might have spoken about first-party, third-party trackers, so let me just give a very brief overview about web tracking itself. Web tracking is the practice by which websites identify and collect information about users. How does it work? Whenever you use the internet, we leave a record of the websites that we visit, along with each and everything that we click. Now, to track this information, normally website users leave certain information either on the browser storage so that they are able to track you. Why is it done? From the perspective of website owners and of trackers, it provides personalization, site analytics, targeted advertisements. Say, for an example, in the context of an e-commerce company, without trackers, it's every user visit to this website could be a stranger, and it's very hard to offer any sort of personalization. Is it evil? Not 100%, but what is evil is its workings remain poorly understood. After you switch websites, normally, advertisements for products that you have recently visited appear maybe in the Facebook timeline or in other advertisements where normally advertisements are sourced. And this happens because of trackers which leave information from one website and all these trackers being connected. The main important thing to know about this whole dilemma is your personal information is valuable, and it's your right to know who is tracking, why are they tracking, and with whom are they tracking, or with whom are they sharing. Now, often the trick is in collecting all of this information and shacking with third parties just to convince you to spend money. Let's look a little bit about what exactly is a first party versus a third party. Say, for example, you visit a website called newyorktimes.com. You chose to visit this website, so we are not particularly interested in all the third-party trackers that might be integrated here, mainly because it's the first party that you're being visited. But under the hood, newyorktimes.com might be connected with n number of trackers, say, for example, doubleclick.net or Google Analytics and certain other trackers. A third-party tracker like doubleclick.net embedded in newyorktimes.com aids this website, the first party, in collecting your user. Now, the third party, anything which is not normally visited by the user directly and which aids the website in collecting all the information associated with this about this website or the user itself is classified as a third-party tracker. Now, the number of trackers that exist in any website depend on the website and on the website owner themselves. Third-party trackers are creepy. This script might look like a normal Google Analytics script, and we as developers often use this. But say, for example, the same script, the g-analytics.com is not really from Google Analytics, but recently this script made news on the web because this particular script, which came from g-analytics.com, aided the owner who bought the script in tracking the credit card information of certain users. So this is why the debt collected or accumulated from using third-party trackers grows, and it often gets enormous. Tracking is not anonymous anymore. Once there is one third party on a page, that has the ability to turn and invite any number of n third-party trackers. In the past, a user's identity would have been unknown, but not anymore. Say, for example, visible third-party trackers like Facebook, the like button from the Facebook page, they can know your identity as long as you're logged onto Facebook. And it is also possible for a tracker to de-anonymize a user by algorithmically exploiting the statistics that are deeply involved around you. Say, for example, your browser version, your browsing history. Yeah, it's statistically possible to de-anonymize the user as long as you're connected to one of the social media networks or just statistically exploiting your possibilities of having all the similarities of browser version, your browsing history, the fonts that you use, and number of other factors which aid. Tracking mechanisms, cookies are the most popular, which are like normally small piece of information embedded in a browser's storage, which are like information less than 4 KB. Normally, when you log into mechanisms which involve a login, they do not require to sign in on the next attempt. That is because of the information stored in cookies. Fingerprinting are deemed to be highly accurate, mainly because of all the information that they are able to collect, such as your browser type and version, operating system version, screen resolution, supported fonts, plugins, time zones, network or hardware configuration, etc. Now, typically, only 1 in a million would have all these possibilities, and that is how they are accurately able to fingerprint and de-anonymize you. Web beacons are normally embedded as hidden images, and they are, as soon as you download, they are able to send information to the server so that they are able to track you, which is why often a good practice is not to download images from emails that you do not trust, because these images are normally web beacons and they actually implant some trackers. If you're wondering how to track the trackers, then I would like to present about Lightbeam, a Firefox browser extension, which I worked last year during my Outreachy internship, which is open source. And using this, it's possible to discover who is tracking you online. Some statistics, as of yesterday, if you visit the Firefox add-on store, these are the statistics for Lightbeam. How many of you use Lightbeam here? Anyone? If not, maybe give it a try. It's open source. Feedback is welcome. And if you're also wanting to get started with open source, I'm happy to chat about it. So when I started this Outreachy internship last year, this was sponsored by Mozilla. Lightbeam was originally a project from Mozilla. And the problem with Lightbeam was it was a legacy add-on. Now, what I mean with legacy is that Firefox from version 57 and above, all the browser extensions had to be written with using the latest, the new browser extensions API. And Lightbeam was, along with many other add-ons, was one of the legacy which was not meeting the latest web standards. So which is why this project was supported by Outreachy, and our main task was to port it from the legacy version to use the latest web technologies and the web extensions API. And also Lightbeam being a visualization which involved a heavy connected graph, the importance was also to improve performance. So when we started, we really had to improve the performance. And we rewrote it in 3 months, and the results were quite good. Just to talk about browser extensions, they are certainly the new frontier, and as web developers, we often would have used browser extensions in one way or the other. A quick poll, or just a quick question, how many of you are not aware of browser extension? Great. So we all use it in one form or the other. The main difference between a browser extension and a web application is that web applications are normally sandboxed to the scripts that they run within the web page that you create or you visit. Now, browser extension has the capability to intercept calls throughout the browser or from all the tabs that you visit, and this is possibly the greatest advantage of having Lightbeam as a browser extension versus a traditional web application. Now, in its simplest form, a browser extension has manifest.json, like a typical mobile application. We need to request for permissions. There are certain scripts which do the job, the name and the version. Each time you publish a new version to the add-on store, the version has to be incremented. And the scripts, say for example, it can be as simple as just set the border style for the document body to 5 pixels solid red. And if you open about:/debugging when still in development mode, it's able to set the 5 pixel border red for the whole web page. So this is how simple a browser extension can be. Now for Lightbeam, the permissions requested are, it is able to intercept all web requests, all URLs, and actively listen to all tabs. Say, for example, a script like background.js in Lightbeam, what it does is it creates a tab when you click the browser action, and it launches a page. So when you open about:/debugging and you load the temporary add-on, you need to load the manifest.json file, and on clicking the browser action, Lightbeam comes into action. For browser extension, there are different scripts: content, background, and page. Content scripts are something like if, as developers, we normally use additional add-ons. I, as front-end developer, like to use page ruler, or just to measure if the page that I build is aligned, or just to get the pixels. And now scripts like these, which are able to act on the website that you visit, are called content script. Page scripts are related to the pages that are being displayed, I'll talk about shortly, and background scripts are the ones which silently listen, collect all the information. And now for these background scripts to listen silently, this is where permissions need to be specified in the manifest.json file. A quick structure of Lightbeam. Lightbeam works by actively listening for, capturing, and storing all the third parties that you visit. All the first parties that you visit and the third parties that might be tracking you. And ultimately, when you click the browser action, it displays the visualization. Now, the listen, capture, and store come under the background script because these do their jobs silently because of the permissions granted when you first install Lightbeam. And when you open the browser action, the visualization shows, and the script which takes care of this is called the page script. Lightbeam doesn't use any content script because it doesn't actively involve with any website. Few things similar to Lightbeam are uBlock or Ghostery, but they don't have a whole historical view, and they work in the form of a content script. That is, once you activate extensions like Ghostery, they are able to show the third-party trackers connected to this website that you visit. Lightbeam, on the other side, gives a whole contextual view of your overall browsing history. The communication between these different scripts, that is background script, page script, or the content script, takes place via asynchronous message passing, or in other words, it uses the runtime web extensions API. Now, for example, in the context of Lightbeam, there is the page script, which draws the visualization, and there is the background script, which captures all the requests. Each one of these, they have event listeners, and for displaying the visualization, the page script would send on runtime send a message to the background script, show me all the trackers that you've collected so that I'm able to display, and it talks to the event listener, which is activated from the background script, and the background script on the other side gives all the information, talks to the event listener. In short, on one side is the visualization, which loads via the page script. On the other side, it's the background script, which silently processes information on the background, and the two talk to each other via asynchronous message passing. The data capture and storage for Lightbeam happens via indexed DB, and the good thing about this is it is asynchronous. Few other things about IndexedDB is it's like a low-level API for client-side storage. It's better than the local storage because you can store lots of information, and given the context of Lightbeam, as the browsing history grows, you can expect enormous visualization and lots of data collected in the browser storage, so IndexedDB was a better choice. And because of its asynchronous nature, it's also acts under the hood via the background script, and it doesn't bother the visualization when the page has to load. The graph, or the next major part of this talk, is about the visualizations. From the legacy add-on, the one thing we decided to continue was to use d3.js and the force-directed graph layout. But the biggest difference, when our focus was to improve performance, the legacy add-on used SVGs, and we decided to replace SVGs with Canvas, mainly to have improved performance. And the first task was to understand how Canvas was better than SVG. Say, for example, we need to draw a drawing which consists of a circle, triangle, and a rectangle. In terms of SVG, each one is a DOM element. But in terms of Canvas, this whole becomes one Canvas element. So certainly, In the case of Lightbeam, where the graph had lots of nodes depending on the user's browser history, and as long as the user never deletes the browser history, we can expect enormous data to be collected and displayed. In the earlier version, because of the SVG, each single element was a DOM, and it added additional load on the DOM. Now, this using SVGs means slow DOM for large data, and it eats too much RAM. But on the other hand, for the canvas, all of this gets displayed via one single canvas element, or in other words, it is one single DOM element, and no additional extra memory is required. But canvas also has its drawbacks. It's not a vector. It's not accessible because it's just one canvas frame, and it needs to be redrawn. Each time you want to update, you have to draw the whole thing. Obviously, this can be improved, but these are the differences when it comes to canvas versus SVGs. In terms of Lightbeam, this is the older version, the legacy add-on, which is no more supported from Firefox greater than 57. But for the given set of graph, in the older version, because they used SVGs, as you can see, each one is an additional DOM element. To represent everything, be it a circle or a triangle or the line, each one has to be represented via SVG. Oh, by the way, this is how the Lightbeam graph looks. The circle is the first party, and the triangles are the third parties associated for the given first party. In the newer version, when we decided to port SVGs to canvas, all of this, the whole element was replaced by one DOM element, that is canvas, and all the drawings were rendered inside this canvas element. Challenges with canvas. Canvas had its own drawbacks, especially when using D3, because D3 is super friendly with SVGs, and using canvas meant no D3 joins. Now, D3 join is a nice way for D3, which automatically takes care of updating or redrawing the DOM. So additional, no effort needs to be taken when new DOM elements get added or new nodes get added. But using canvas, we had to fall back and write other methods. And because of canvas, interactivity was a problem. As already mentioned, canvas was one whole piece of element, and it was not accessible. The next thing is about data to graph. As I mentioned already, Lightbeam works by listening for, capturing, and storing the data. So then the data needs to be converted to the graph. So for this, we decided to use D3's force layout algorithm, mainly to get all the simulations associated with this, which kept the graph in position, and drawing on canvas. The force-directed graph layout works as follows. To really debug this, I had to understand how gravity worked in real physics environment. So we had a graph, and it was quite interesting to learn all the aspects that it took to position a node in center, or to make sure that no two nodes collided, or just to make sure the nodes always repelled and they never attracted. The force layout algorithm, it creates a simulation for an array of nodes and links, and it composes the desired forces. Now, the nodes and the links are the ones given by the background script. And then the force layout algorithm gives the associated position where the graph needs to be drawn, and that's how it is transferred into a canvas. Debugging the force layout, which was my interesting topic. So to start with, the draw function, it took in the nodes and the links from the background script, and there was a simulate force function, which simulated all the physical simulations from D3's force layout algorithm. To start with, D3.force simulation, what it does is it initializes the simulation during the page load. For given each node, that is the first party or the third party, it computes the nodes, the current XY position, and the velocity, that is with the velocity, with what velocity it has to move. So in this image, if you see, so when the page is loaded, there is certain X and Y computed, and the physics simulation comes in picture, and because of the velocity calculated by the force layout algorithm, it makes a nice animation. And this is how it looks in stored in indexed DB. Each node is classified as a first party or a third party. And there is the X and the Y position, and the Vx and the Vy, that's the velocity by how much it has to move. And then, once all these are computed, it's easy to transfer this onto a canvas, because we now know where each node has to be positioned and by what velocity it has to move. So this is what I meant when I said we decided to use D3's force layout algorithm only to compute the X and the Y, the positions and the velocities. And all of this was then transferred to a canvas. The next thing was the tick function, or in other words, we had to register the simulation's internal timer, and this did a redraw each time on the canvas. Using SVG, this is where SVG has a nice D3.joint mechanism. You don't have to redraw, but the joints take care of automatically updating and displaying new nodes similar to the virtual DOM what React has. Now the tick function, because of physical simulations, they go on ticking till the graph achieves equilibrium. That is, till the graph attains a balance. Or other words, it keeps trying to compute the velocities for the X and the Y position, and the graph keeps moving. So it's very important for the graph to attain equilibrium. The next one was to register the simulation forces, and this took care of the dynamic node additions to the graph. The first one in the registering for the simulation force was to understand how to center the graph. In the absence of this centering force, what happened was, as you can see on the top left, the nodes were just displayed on the top left because the centering force was missing. Now, when the centering force was applied and the page was loaded, all the nodes were centered with respect to the display area. The next thing was to register the position forces, or in other words, when new nodes added, at what position should they update on the graph? For example, if you see this GIF, you can see a movement starting from top left to the center. That is, when the page is loaded, by default, it starts from 0 and 0, which is the top left of the graph, because the position force themselves was missing. On applying the position force, and if you carefully observe the second GIF, and when the page is reloaded, the graph just opens up from the center, because now there are two forces acting. One is the center force, and the other one is the position force. The position force normally tells at which position should the new nodes be updated or displayed at. And all of these computations come from the D3's force layout algorithm. The next one was the charge force. Charge is like to simulate gravity. It simulates attraction if the strength is positive. If the strength is negative, it simulates repulsion. In our case, we have a strength of -100 because we do not want the nodes to be cluttered. We do not want the nodes to be attracted, but when the page opens up, the nodes have to repel. So in this case, this is initially is the attraction but on page load, it repels because of the negative strength that is given, and the nodes all repel against each other. So these are all like quite interesting topics which directly deal with physics, gravitational forces. The next one was about the collision force. It prevents nodes from overlapping by detecting collision around the specified radius. In the first example, you can see this node is colliding, or in other words, overlapping with other nodes. Now, to prevent this overlap, the collision force had to be registered, and in this case, no two nodes will ever overlap, and this is taken care by the collision forces. The other interesting thing was a collision radius of 30 drew a graph like this, whereas a collision radius of 10 drew a graph which was much neater. The nodes were more compact. After doing a lot of debugging and really understanding how gravity works and how to simulate all these physical simulations via D3, the outcome was quite nice. It was a connected graph, a huge connected graph, which constantly grows depending on the browsing history. And the animations themselves, they show up on page load, and they make sure that all the forces are applied, and it really it blows up. The nodes repel, they are all centered. Everything was good. The next thing was to really understand about the simulation's internal timer, about the tick-tick-tock function. So it was very important to understand when the graph really attained equilibrium, or when all the forces stopped applying to each other. And this was important when I finally figured out that the tick function stops when alpha reaches 0. So by default, alpha starts from 1, and it computes all the forces that you have given it to compute. In our case, we had the centering force, the position force, collision force, and the strengthening force. So alpha works in a way it started from 1 and goes all the way up to 0. The algorithm, it starts with the default value of alpha. It decrements the node's velocity by a certain position, and the nodes keep moving. Via all the iterations, it finally gets alpha to 0. Until then, the nodes keep trying to balance themselves against each other, and they finally stop when the alpha has reached 0, which tells the algorithm not to recompute additional forces, but to stop. We also had a case when the graph just like was computing, and the nodes finally disappeared. So it was really important to understand what are all the default values, how the algorithm really worked. So in this case, the graph starts, and finally, after all the simulations are applied, the animations, they finally stop in this case, and it means it has achieved equilibrium. Or in other words, alpha has reached 0. These are the values which are computed eventually via the D3's force layout algorithm, and that's what is being mapped to draw on the canvas. The next interesting case we had of dynamic updates. So everything was fine. The nodes were getting loaded. The graph was simulating well. It was a nice animation. But we had a case. So in this case, the graph has achieved equilibrium, which means the D3's algorithm sleeps, or it doesn't do any more computations. And the background script was processing new information, and because of the asynchronous communication, it asked this paid script to load new nodes. Now what is happening here is the graph itself is no more computing. Alpha has reached 0, but when new nodes were added, they started again from the top left, that is 0 and 0. The question was, the centering force was applied, the positioning force was applied, but it took a while to really understand that all of this worked until the way that alpha was 0, but to really get the simulation to restart, we had to reset the value of alpha. And on resetting the value of alpha again to certain values, you can decide from 1 to 0. It doesn't have to go all the way from 1. When the graph is heavy, starting all the way from 1 can be quite hard for the computations themselves. So it really depends on what sort of animations are needed or how much computations need to be done. So it also can be that alpha is enough that it's just set until 0.5 to 0. But really, the trick was to reset the alpha. So in other words, just to recap what all that I said, the problem we had was the background script processed all the information. We had the nodes and the links. And then we had to simulate a force layout, because this is what we were using D3's force layout algorithm. And then D3.js was quite handy. It said, OK, I can run the force layout algorithm. And it did the force simulation. The tick-tick timer was quite good. Everything was fine. The tick-tick timer, in the meanwhile, it kept on updating the x and the y values, at which position a node has to be positioned initially, and at what velocity should the node keep going. And the tick stopped finally when alpha is 0. It started with alpha 1 and went all the way up to alpha is 0. The next thing was the D3 said, yes, I've computed all the coordinates. The canvas is now good to be redrawn, and everything was fine until we got the dynamic nodes condition, in which case there was a new node, and I had to update the graph, but the new nodes started from the top left corner. And in this case, the problem was the new nodes really started from top left, and it was like, OK, how do I debug? And the trick was in understanding how the alpha really worked. So alpha is 0, and that is why we had to reset the simulation. And on resetting the simulation, the graph, again, was no more in equilibrium. It started again to rebalance, apply all the forces, and the graph looked good again. So this was really insightful to debug the underneath of D3's force layout computation. And the maths is also quite fascinating. It really uses Newtonian integral calculus, and things were really cool there to really study what's happening. The next thing is about canvas-based interactions. As I mentioned, Canvas had its own challenges. It's not a vector, it's not accessible, and it's just one frame. So for interactivity, we had tooltips. Now for tooltips itself, each the mouse coordinate had to be computed, which itself is not such a difficult task. But on the other hand, this task would have been simpler if this was an SVG, because you exactly know where this DOM node is located, and it's easier to show the tooltip. But when the graph is huge or like quite dense, computing tooltip is another additional overload. But it had to be done. So the way it was done was, wherever the mouse moves, if there was a circle detected, so it's like simple mathematics being used. If there is a circle located in this vicinity, then yes, it's a first party. Or if it's a triangle located in this vicinity, then it's a third party. Those were the computations which went under the tooltips. The next thing for interactivity, Lightbeam supports the drag, zoom, and the pan. Quite interesting about D3's zoom is it draws all the zoom in the Z coordinate, and the drag and the pan happen in the XY coordinate. So for the zooming and between dragging and panning, it had to be translated from the Z coordinates onto the 3D coordinates onto the 2D coordinates. Let's talk about performance. When we started this internship, The main idea was there were two tasks ahead of us. One is to port the legacy add-on to use the new browser extension API. And the next thing was to improve the performance. So this is the legacy add-on. For the given set of websites, as I already mentioned, the circles are the first parties, the triangles are the third parties. It is a connection of all the related trackers that are connected. In the legacy add-on, for the given set of websites, the graph took about 23 seconds to stabilize or to reach equilibrium by applying all the computations. And during this duration, there was an average of 31.23 frames per second. On the improved version, Lightbeam 2.0, for the same set of websites, the graph took about 14 seconds to stabilize or to achieve equilibrium, which is quite good. And on an average, it had 46.29 frames per second. This definitely can be improved. In the first run, this less frame rate is mainly because of all the additional computations which went in to translate from the 2D coordinate, from the 3D to 2D during the mouse interactions, or to compute the tooltip for each node itself. So performance-wise, considering given this was a 3-month internship, we were quite happy. We reached what we were meant to do. We converted Lightbeam to use the latest web extension API, and the performance was good than the earlier one. The next thing was about to further improve the performance, and the idea was to use web workers. Web workers are scripts which operate in the background in a separate thread so that the main execution, the UI execution, is not blocked. And the idea was all the D3 computation and all the additional math which went to compute the canvas interaction to put in web workers themselves. Or in other words, the graph doesn't redraw on the canvas every time, but it just draws when it has the final computation values, thereby reducing the load on the main UI thread. The performance was quite good over here. As I mentioned, this was just the beginning of me getting started with open source. So last year for MozFest, which happens annually, which is a Mozilla festival, which happens annually every year in October, I built a version of Lightbeam in A-Frame. And the idea was for the participants to interact with the trackers in the VR world. The whole idea of Lightbeam is to educate the general public about privacy and why is it important. And given the fact, the recent scandals that happen with the top tech giants, it's very important that we all understand what privacy is and how can we tackle this. The next steps, Lightbeam, I'm still continuing to work on Lightbeam. So at the moment, I have an open source grant from the German government called the prototypefund.de, which supports projects, and it's supported by the Federal Ministry of Education. And I'm collaborating with researchers from Tilburg University, Netherlands, who are working on a data justice project. They are trying to understand trackers from different parts of the world and how they behave. So we are hoping to have some public results released in early 2019, or around May 2019. So I'm quite happy with where all of this is headed to. And if ever you want to understand how all of this works, I'm happy to chat or tell more. There are a lot of resources, articles on Medium, which I've written about web tracking, on my blog. I also underwent the Open Leaders program for Lightbeam. Yeah, the whole idea is to just educate everyone why privacy is important and how we can take care of it. credits to the slides. And thank you. I am done. We are also looking at Smart Helios. We're looking, it's a small team, so if anyone is interested, talk to me if you want to relocate to Berlin. And otherwise, thank you for the time. And I'm happy to take questions, or I can be reached on social media. Thank you. Thank you for listening.
So now you can ask questions. If you can't ask them in English, but can tell it to me in Russian, I'll try to translate. Okay.
Thank you very much for a very nice presentation. I'm Khachatur from Armenia. So my question is, in spring, as you most probably know, the GDPR was released, the General Data Protection Regulation. And after that, the user needs to agree or disagree whether its data will be tracked by third-party application. So my question is, does Lightbeam checks whether the agreement was done or disagreement was done, and does it show only the agreed third-party trackings, or it just shows what can be tracked?
No. Lightbeam at the moment doesn't do any of that, but Firefox by default has this tracking protection which you can toggle on and off, but Lightbeam is not, no, it doesn't detect if websites violate the privacy. But there are like certain tools, and also in the latest, the data justice project which I mentioned, we are hoping to tackle this problem or like present some results or how the trackers on which parts of the country they violate, and we are hoping to present these results. So it is quite fascinating for me as well to really understand all the risk or all the things that go under the hood, and we just take all these things for granted. But yeah, that's where I'm continuing all this work for Lightbeam. But at the moment, no.
Hi, thank you for your talk. And I was wondering if those triangles that represent the third-party websites that track information, do those triangles interactive, and do they display like what kind of data is being stored or is being gathered about the user? Thanks.
Again, no. For now, it's just like it's a first party, and the triangle is a third party. So, and again, when we talk about third parties itself, there are like different third parties. So, say for example, certain e-commerce websites, they have in-house third-party tracking tools, which again are like not really third parties. And at the moment, Lightbeam is not able to classify these different kind of third parties themselves. The main idea for Lightbeam is, on the nutshell, just present the overall picture. So yeah, we yet do not go that deep with Lightbeam. For now, no.
Hi, thank you for your talk. I didn't get, why did you make the Lightbeam for Firefox, not for Chrome, for example, because Chrome is obviously more popular. Thank you.
The legacy add-on, as I mentioned, was working only on Firefox. So when we ported, we used the latest web extension API, which also works in all the modern browsers. It's just that the legacy add-on was Lightbeam, which was a Mozilla project, and which was supported by Firefox. So the logo is like Lightbeam by Firefox. But it's not put in on the Chrome store yet. But if you go to the GitHub page, download, and try to run it on Chrome, it does work.
Have a nice day. Thank you for my question is, when you have 1,000 nodes, then performance become matter. So how you resolve what to use, Canvas or SVG?
Yeah, so this new version just uses Canvas for the whole thing. There are no more SVGs, which is why it's quite good to take like quite a lot of load. But it's still slow when the nodes really go above like 8,000 or like 10,000, which is why there is an alternate approach to do all the computations via web workers, which is like, which hugely improves the performance. But in this version, there are no SVGs, and it's Canvas for everything. It doesn't depend on if there are fewer nodes, we use SVGs, and if there are greater nodes, we use Canvas. The older version used SVG, but the rewrite is purely Canvas.